Okay, so welcome everyone. I am Jack Haddad. I'm an assistant professor from Technion, Israel Institute of Technology. Today I'm replacing Chao Li, the organizer of the webinar. Um, it's my great pleasure to host the traffic flow theory and characteristics ISTTT webinar series. Um, Before we start, I just want to just to let you know that I recommend to turn off the microphone. On the right hand side, you have a control panel. So the default is that the microphone is in green and on. So please turn it off, unless if you want to ask some question during the presentation. So today, without any further delay, we would like to start. So today, the title of the lecture is Stochastic Optimal Path Problem with Relays. And it will be given by Will, right? Will Chin.
Yes.
Will is a PhD student in the Transportation System Analysis and Planning at Northwestern University, and his research is focused on transportation network design, modeling, and optimization. So, without any further delay, please, you can start.
Okay, sure. Hello, everyone. Today I'm going to present the stochastic optimal path problem with relays. So this work is a joint work with my advisor, Professor Mark Goulier from Northwestern University. So this paper studies the optimal path problem for vehicles with a limited range, such as most electric vehicles currently available in the market. For such vehicles with a limited range, if the trip distance exceeds a range limit, the vehicle may have to be refueled at designated stations to continue the trip. Since a feasible path may thus consist of several relays, this problem is called the optimal path problem with relays. And here is an illustration. So in this small example, the load R is the origin and the load S is the destination. And there are some normal nodes in this small network, and also there are some relay loads. And you can think of relay loads as charging stations for electric vehicles. So for the traditional gasoline vehicles, the vehicles can go directly from the origin and go through some normal loads and then go to the destinations. But for the vehicles with limited range, if the trip distance is too long, they may have a risk of running out of fuel en route. So they may have to go through a few relay loads to refuel. And then through a sequence of relay loads, they can eventually go to the destination. Here is a difference between the traditional gasoline vehicles and the vehicles with limited range. And in transportation, this problem has attracted attention recently, thanks to its role in supporting the transition to alternative fuel vehicles. And the primary challenge to the adoption of most alternative fuel vehicles is that the lack of a dense network of refueling stations causes range anxiety. That is, drivers worries of running out of fuel en route. A long-term solution to the problem of range anxiety is to optimize the design of the refueling stations. In the foreseeable future, however, the drivers of most alternative fuel vehicles would still face limited refueling options. And in this circumstance, careful routing decisions that integrate travel cost minimization and relay requirements will contribute to the positive user experience, hence the adoption of alternative fuel vehicles. And the literature on the optimal path problem with relays is relatively sparse. And most existing studies tackle this by taking advantage of the fact that an optimal path must consist of a sequence of optimal subpasses between relay loads. And accordingly, this approach divides the original problem into two stages. So in the first stage, the optimal passes between each relay load pair and are obtained by solving a weight-constrained shortest path problem. And then these optimum passes are used to create an auxiliary network that contains only the relay loads. And in the second stage, the optimal refueling decision is determined by solving a standard shortest path problem on the auxiliary network. And the computational challenge here is to solve the weight-constrained shortest path problem efficiently, and which has been studied extensively in the literature. And the second approach is to use one-stage labeling algorithm. And the labeling algorithm updates the labels backwards from the destination to the origin, and during the updating process, line-dominated labels are kept for each node. And after the updating process is finished, the optimum path can be retrieved. And in the optimum path problem with relays, the range of the vehicle plays an important role. And we know that the fuel efficiency, hence the maximum range of a vehicle, depends on the average driving speed, which in turn is highly correlated with the prevailing speed of a road on which the vehicle is operated. And consequently, the vehicle's range is also affected by the traffic conditions, which vary substantially due to unexpected demand surge and the supply disruptions. So optimum path finding under such uncertainty has been well documented, especially along the line of optimizing the travel time reliability. Yet uncertainty could have much worse consequences for alternative fuel vehicles drivers than longer than expected delays. And specifically, a suboptimal route obtained without considering the impact of uncertainty could substantially increase the risk of failing to reach the next relay point. And to the best of our knowledge, few had examined how this risk may be incorporated into finding optimum path problem with relays. And so in light of this gap, this paper proposed a stochastic optimum path problem with relays, which aims at minimizing a general expected cost while maintaining a reasonable probability of arriving at a destination. So in this problem, stochastic traffic conditions are considered by treating the travel speed as a discrete random variable. And we also proposed a range speed model for electric vehicles. And we use a two-stage label correcting algorithm to solve the stochastic optimum path problem with relays. And we also conduct several numerical experiments to illustrate the properties of our algorithm and the computational efficiency of our algorithm. Now I will present the range speed model. We focus on the electric vehicles because of two reasons. So first, electric vehicles are the most representative among the range-limited vehicles. And the second reason is that the energy consumption of electric vehicles is not affected as much by acceleration as conventional gasoline vehicles. And specifically, we model the energy consumption per unit distance for electric vehicles as a function of the prevailing driving speed, and as we can see here in the equation 1. So there are basically two items in this equation. The first item has to do with the attractive power used to move the vehicle, and we're assuming like zero acceleration here. And the second term is related to the power draw of accessories. And with this equation, and we can get the range of a vehicle. So for a battery with maximum energy EM, the range is basically the maximum energy divided by the energy consumption per unit distance. And here we plot a typical range speed relationship for an electric vehicle. So we can see that the figure shows that the maximum range reaches a peak value of more than 120 miles at the speed of when the speed is around 30 miles, and almost 3 times as high as the lowest range achieved at the very low or the very high speeds. And we know that the actual shape of the range speed curve may be affected by many features of the vehicle, and could deviate from what is illustrated here in this figure. And however, this figure is enough to say that the range is indeed affected by driving speeds substantially, and this relationship should be taken into account when planning relay and routing decisions for range-limited vehicles. And we want to emphasize here that the proposed modeling framework can accommodate any range speed model, not limited to this one specifically here. With this, now we need to introduce a concept of ideal distance. So we start below the optimal speed that maximizes the range, and accordingly, RV star is called the range limit. So for modeling convenience, we define the ideal distance corresponding to a distance of d traveled at speed v as RV star divided by RV times d, and it is shown here in the equation 3. And this ideal distance can be interpreted as the equivalent distance traveled at the optimal speeds. We start with the same energy consumption. And know that the ratio between the ideal distance and the range limit measures the percentage of energy consumed by traveling distance d. So with this ideal distance, we can measure how much energy is being consumed by traveling the link. So with this range speed model as an ideal distance concept, we can now present our optimal routing model. So first, a few assumptions and few annotations and assumptions. So in a directed network, GNA and N and A are sets of nodes and links respectively, and the set C denotes a set of designated refueling nodes. And the general cost of traversing a path K is defined in this equation 4. So basically, it has two parts. The first part is a energy cost, and the second part is a travel time cost. Here is energy cost per unit ideal distance, and alpha t here is a value of time. And Vij is a discrete random variable for the traveling speed on each link. And this random variable can take one of the discrete values defined in the set, and each value is associated with a probability. So the sum of the probability is equal to 1. And another assumption is that if the vehicle needs to be refueled at the refueling node, and it is always refueled to its maximum energy level, and the cost for each refueling is defined as in the equation 5. So the gamma 0 here is a fixed cost for each refueling, and Z here is a refueling time. So some variable cost has a linear relationship with the refueling time. So now here is a problem. So consider a trip between an origin and a destination S with the distance beyond the range limit RV star. So the problem is to find operating policy such that the overall cost is minimized, while the probability of arriving at a destination S is above the given threshold, PLB. So we divided this problem into 2 stages. So in the first stage, an all-to-one optimal routing problem is solved repeatedly for all the refueling nodes and the destination node. And for the optimal routing problem in stage 1, a low refueling is allowed. And for each node, each refueling node or the destination node, we use mu ijr and fijr denote the expected cost and the probability of arriving at the node X and starting from I while node J with the remaining range R. And the updating process starts backwards from the destination to the origin. And we note that the updating process will terminate immediately if the probability threshold is not satisfied. So with this, we can improve the computation open path problem in the first stage. So and also the all-to-one optimum path problem for all the refueling nodes could be pre-processed to improve the computational efficiency. That's because if we need to solve another OPPR for the optimal path, we don't need to solve the optimal path for the refueling nodes again. We can use the existing results because those passes do not change for different OD pairs, for different like origin destination OD pairs. And here is the updating formula. Basically, it's a dynamic programming and the labeling algorithm. And we can prove that the routing policy generated by this updating formula is optimal. But due to the time limit, I won't explain the details of the proof here. So in the second stage, with information obtained in stage 1, an auxiliary network is built. And the link in the new network represents the optimal routing policy in the original network. And in this auxiliary network, we have 4 types links. So the type 1 link is from a feasible node to a node in set C. We recall that the set C is a set of designated refueling stations. So the type 1 link is linked from a feasible node to a refueling node. So the type 2 link is linked from a refueling node to a refueling node. So this link connects to refueling node, so the vehicle can go can extend its range. And the type 3 link is a refueling link or a refueling load from refueling node to destination, and type 4 link is a link from a feasible load to the destination. And after we have this auxiliary optimal routing problem is solved again, and this and the updating procedure is similar as a one in stage 1, and the updating formula is also similar. So the resulting optimal path connects the origin and the destination through a sequence of refueling nodes, and the complete optimal routing policies can be retrieved by combining the results from both stages. So here is an illustration example to explain how we create the auxiliary network. So the figure in the upper is a small network containing several. The node R is the origin and node S is destination, and the node 5, 9, 11, and 13 are refueling stations. And the graphs under the bottoms are the links associated with refueling node 13 and the destination S in the auxiliary network. And we can see a link between node 4 and node 13 is created, and which means the driver can reach node 13 from node 4 without refueling with a probability above the threshold, at least when the vehicle has a maximum range. And moreover, we can see the link from node 4 to node 13 is a type 1 link, that is to say is from a feasible node and to a refueling node. And node 5 to node 13 is a type 2 link. It's from a refueling node to a refueling node. And node 12 and in the right graph, and node 12 to the destination S is a type 4 link. Is from a feasible node to the destination. And also we have the node 13 to the destination S. So actually it's a type 3 link. Is from a refueling node to the destination node. So with the auxiliary network, the long distance trip becomes available because the vehicle can go through the refueling nodes to refuel and extends its range, and thus eventually go to the destination. And we also conducted several numerical experiments. So the numerical experiments are coded using TNM. This is a C++ library for network applications, and it's developed by my advisor. It's tested on a desktop with this configuration you can see here. So we tested 2 networks. So first is a small hypothetical network, and the second is a sketch network of Chicago region. we call it Chicago sketch network. And here are the parameters used in the numerical test. The time value is $15 per hour, and the electricity cost is 3 cents per mile, and the fixed cost for each refueling is $5, and the variable refueling cost is $0.15 per mile. And default probability threshold is set to be 0.8. So here, first it's a small network, and we set the range limit to 25 miles, and we use 8 different speed values ranging from 10 miles to 80 miles. So it's actually the same network as in the previous example. And here are the results. So we computed the optimal passes for both the deterministic case and the stochastic case. So the stochastic case is a proposed model in this paper, and the deterministic case is just a traditional one without considering the uncertainty. And we can see the two passes are quite different. And in the deterministic case, the vehicle is only refueled once during the trip. And for the stochastic case, the vehicle has one more refueling, and consequently, we can see the cost for the deterministic case is lower, and the arrival probability is of course 1 because there's no uncertainty. And in the stochastic case, we can see the cost is higher because of the 1 extra refueling, and the probability is below 1, but is above our probability threshold. So from this example, we can see the importance of considering the uncertainty in the road network. And we want to emphasize here is that the path is from R to line, and from line to 11, and from 11 to the destination are adaptive policies that depend on the remaining range when the vehicle arrives at each node between these two nodes. So to demonstrate this, we take a realization of the adaptive path between node R and node line as an example. So in this figure, we can see a driver starts with full range 25 miles at node R and moves to node 1 based on the optimal routing policy given by the first stage algorithm. So the actual distance, and we can see here, the actual distance from node R to node 1 is 3 miles, but due to stochastic traffic conditions, the ideal distance could be larger than 3 miles. And in this example, the drivers arrived at node 1 with a remaining range of 21 miles. That means the ideal distance between node R and node 1 is actually 4 miles. So according to the optimal policies at node 1, the driver should continue to node 4 and 5 the next, and eventually arrives at the refueling node line with a remaining range of 8, and we can see here. So then the vehicle will be refueled to full range, and the driver will continue to follow the adaptive policy to travel from node line to node 11. So worth emphasized here is that since the ideal distance varies with random speeds, so many possible passes from node R to node line could emerge according to different realizations of speeds. So the path shown here, the adaptive path shown here, is only just one possibility. So this small example demonstrates how the optimal policies generated from solving the stochastic optimal path problem may be used to produce routing and refueling decisions for the drivers of automotive fuel vehicles. And it also highlights the importance of considering uncertainty, because it could completely change these decisions. And here is a larger case study in the Chicago sketch network. So the Chicago sketch network has about more than 900 nodes and almost 3,000 links. And we set the range limit as 50 miles, and the trip distance is around 80 miles. So this case study is constructed with the application by drivers of currently available electrical vehicles in mind. So since chargers are often available at dealers that sell electric vehicles, and given the popularity of Nissan Leaf, we choose the Nissan dealers in the Chicago area as potential refueling locations. So here we can see in the figure on the right. So the node R is orange and node S is a destination, and the node 1 to 20 are the refueling stations in our example. So actually, they are also Nissan dealers in the Chicago areas. So here are the results for both deterministic case and the stochastic case. And so the path 1 is the optimum path in the deterministic case. And we can see in the optimum path, the vehicle refuels twice. And in the path 2, the optimum path for the stochastic case, the vehicle refueled 3 times. So as expected, the cost in the stochastic case is higher, and the arrival probability is 1 in this case. And we also computed the arrival probability of path 1 in this, and we found that the probability is below the threshold. So this example says that, so if the driver use path 1 in uncertain conditions, the driver is running a high risk of not being able to arrive at the destination. So this example again confirms the importance of considering uncertainty. And we also examine the sensitivity of the optimal refueling passes with respect to different parameter settings. And the first table is sensitivity results with respect to the probability threshold. So the first column is the probability threshold from 0.5 to 0.9. So we can see as a probability threshold increases. So at first, the optimum path does not change, and the expected cost does not change much, but the arrival probability changes. And as the probability continue increase, we can see the optimum path is more refueling because some of the paths have the probabilities below the threshold are eliminated. So the vehicle needs more refueling to satisfy the probability constraint. And we can see the expected cost increase a lot because of more refueling. And the second table is the sensitivity results with respect to range limit. And the range limit is in the first column from 40 miles to 100 miles. And we can see in this case, it seems the results change substantially, like from when the range limit increased from 40 to 100 miles. And at first, when the range limit is very low, you need many refuelings to achieve to satisfy the probability threshold. But when the range limit increases to 100 miles, and we can see the expected cost decreased dramatically, and the arrival probability is also 1. You only need 1 refueling. And to better understand the cost sensitivity with respect to different parameter settings, and this figure plots the average expected cost of the 15 randomly chosen OD pairs versus different probability thresholds and range limits. And the figure on the left shows that the average expected cost remains flat when the probability threshold is less than 0.7, but it increases quickly as the threshold grows beyond 0.7. And the figure on the right that the average expected cost increases nonlinearly and almost monotonically when the range limit decreases from 100 miles to 40 miles. So comparing these two plots seems to indicate that the optimal user cost is more sensitive to the range limit than to the probability threshold. However, it has to do with topology of the network. So maybe in other networks, these results cannot hold. Okay, finally, we also examine the computational performance of our algorithm. So in our tests, the the stage 2 algorithm almost consumes the low CPU time compared to what it takes to run the stage 1 algorithm, because the stage 2 algorithm operates on a much smaller network. And for this reason, we only report the average performance measures for running the stage 1 algorithm once. So first is average CPU time with respect to different probability threshold. So here's the label size here is of land-dominated labels kept for each node. So we can see the average. So we can see the CPU time drops as the probability threshold increases. The reason is that fewer nodes can satisfy the probability constraint as the probability threshold increases. So because of this, the stage 1 algorithm can terminate early because it does not need to update all the nodes in the network. And the label size shown in the figure on the right also decreases when the probability threshold increases. And this graph on the left shows that the CPU time increases with number of discrete speed values, and while the average label size decreases. The increase of CPU time is likely a result of calculation involved in the main updating formula. And finally, we can see the CPU time and the label size, average label size in the first stage increases almost linearly with a range limit. This is expected because more nodes and range intervals will satisfy the probability constraint with a greater range limit. Thus, more calculation is needed to finish the first stage algorithm. So to summarize, the computational performance of the proposed algorithm does not seem to be very sensitive to the input parameters tested in this experiment. So importantly, the average size of the dominated labels does not seem to increase exponentially with these parameters. Also in theory, they could. So calculation time is excluded. The total CPU time for the Chicago sketch network never exceeds a couple of seconds in all the tested scenarios. And here are some findings from numerical results. So from the numerical results, we can see the deterministic and stochastic models lead to quite different refueling decisions, which highlights the impact of uncertainty and the consideration of arrival probability. And the second is different probability thresholds and range limits may lead to different optimal passes. So in general, the range limit has a greater impact on the expected travel cost than the probability threshold. And also the optimal path problem in both stages involve land-dominated decisions. The label correcting algorithms scale quite well. Notably, the size of the land-dominated labels kept by the label correcting algorithm is relatively small, even for the Chicago sketch network, and is not very sensitive to the input parameters such as the arrival probability threshold and the vehicle range limit. Okay, so this is what I have today, and thank you. If you have any questions or comments.
Okay, thank you, Will. Thank you for this interesting presentation and talk. And actually, it's a really interesting research topic. If somebody has a question, he can turn on the microphone and ask it. Or otherwise, you can write your question on the chat box. Is there any questions? Okay, actually, I have one question. Meanwhile,
Sure.
So just to be sure, you assume that the refueling stations are the position of the refueling stations are known in advance, right? So in your example, you were showing the network like node 3 and 9 and etc., right? So,
Yeah.
so my question would be, will you consider to extend this work in order to take into account that the locations, I mean, it's something like you optimize the locations of the refueling stations in this current
Oh,
framework?
yeah, I know. So you need optimize the location of the charging stations, right?
Yes.
I think it's a different problem. So yeah, my advisor has another student studying this kind of problem, but I think it cannot be addressed like simultaneously with the um, calculation of the optimal path problem. So maybe we need to define a larger objective function to optimize the location of charging stations and using this kind of uh, optimal path as an
Okay. I
optimal path problem as an input, right?
Yes, I understand. Okay, now I understand. But so then, can this framework be utilized for real-time optimization? For example, during your trip, you get some information that, for example, node 9 or a location refueling station 9 is full with cars. So they send you information, you cannot come in. So in this case, you will have less stations in your pass. So can you do it in a real-time optimization?
I mean, in the real time, I think if there are new information such as traffic condition changes, we have to recompute the algorithm
And this is
to get to the new.
and this can be done easily because I think because the computation time is very low.
Yeah, yeah, I think so. Yeah, it has a potential to do the real time like routing.
Okay, okay, that's interesting. Is there any more questions? Please feel free to ask or to write in the chat box. Okay, meanwhile, I have another question. What is your future research? What is you're focusing on?
Uh, and current research is to do with the design of a flexible transit system. So basically, so the system works like this. We have fixed routes, and we also have flexible routes running around the fixed routes. And the flexible transit vehicle can pick up passengers from origin and deliver them to the transit station. And then they can also pick up passengers from transit station and deliver them to the destinations. So this is my current research is the design of a flexible transit system for low demand areas.
Okay, okay. So if there is no further question, I close this presentation talk and thank you very much. And I hope to see you all and more people for the next presentation and talk that will be, I think, in 2 weeks in this ISTTT series.